And this is 6.3, the gamma lesson. And now we've got additional conditions, which is what we're focused on here. So this thing we saw last week, the population has to be greater than 10 times the sample size. And the reason the population, that's a condition for inference, is because we're sampling without replacement. And the binomial algorithm is based on with replacement. There's an example in the book where they have the sample that's more than 10% of the population, and they show you how much it's off by. The issue is this, that when we get to conditioning, or I'm sorry, when we get to inference, you're going to have to identify the conditions and verify. These conditions are new. N times P hat. Let's make sure we understand. P hat is the sample proportion. If it has a hat on it, it's telling you it comes from the sample. I know there's a lot of different symbols here. If you don't understand it, you've got to ask. So N times P hat has to be greater than or equal to 10. And N times 1 take away P hat has to be greater than or equal to 10. Well, to be safe, in May, you should verify both. But it makes sense to you that you like to verify the smaller one. So if P hat's 40%, then if this one's greater than or equal to 10, then that one has to be. That'd be 60% times N. But don't be presumptuous. Like a reader knows that you saw that. Check both of these. And what do these go to? These go to the shape of the distribution. So if you go to your textbook, look on page 420. And on 420, there are 3 graphs from left to right. And in the first one, ready, you have N is 10. The sample size is 10, and the proportion is 8/10. Well, 10 times 8/10 is less than 10. 10 times 2/10 is less than 10. And you see the shape of that graph. They fit a curve to it. So the second one, N's 20, proportion's 8/10. Well, 20 times 8/10 is 16. That's bigger than 10. But 20 times 2/10 is less than 10. So that fails the condition. You get to the third point, the sample size is 50. 50 times 8/10 is 40. 50 times 2/10 is 10. And you can see how the picture on the right, which is the minimum sample size to meet the condition, fits the curve the best. So you've got these conditions. This one deals with, from last week, the fact that we're sampling without replacement, and these conditions deal with the shape of the distribution. Okay? Now, you don't have to explain that on the AP test. You just can't omit conditions. You get an inference problem where you have to, we'll give you the outline of what you have to do for an inference problem. But a lot of people just say, oh, here's my p-value. I'm going to reject or fail to reject. They may be correct. They're getting very little credit unless they follow all the steps to the inference. Okay, so we're introducing you those steps now. So there's 2 questions, 99 and 103. We're going to pause the video. You're going to those 2 questions, and we'll come back to those solutions. Okay, so the data set for 99 and 103 is the same data set. So we're talking about left-handed students in a large high school. 99 is doing the problem from a binomial distribution. Well, the actual data is discrete. You have to have a whole number of left-handed students. But 103, if it meets the conditions, we can do a normal distribution to approximate this. So for 99, first thing is, can we do this? Well, the population is greater than 10 times the sample size, meaning what? It says a large high school. So you're assuming a large high school has more than 1,000 children. Make sense? So if your sample size is 100, it's less than 10% of the population. For a binomial distribution, we're saying binomial CDF, remember this is discrete. So we're going to go up to and including 14% out of 100, and then do one take away that. So we're getting up with 13%, a little more than 13%. So on the calculator, we're here. We're going to get the same answer. If I go here, second distribution, binomial. Now, careful, you want cumulative, not CDF. So we click on this. What are we doing? We have 100 trials. The probability for success is 0.11. We want everything up to and including, ready, because it's cumulative? Well, let's do this, not 0.11, 11, sorry. Proportion success is 11%. We want everything up to and including 14. Because the question says, what's the probability that at least 15 or more are left-handed? That's our answer, which is what? That's a probability that less than 15 are left-handed. So the probability that 15 or more are left-handed would be one take away the answer. Logical? All right, so we say that the likelihood that we get that many left-handed children in our sample is a little more than 13%, which is not statistically unlikely. And what? Well, now let's deal with this from a normal distribution, which is continuous. Well, the conditions are met. Because the probability of success is 11% times 100. It's greater than 10, and 89% of 100 is greater than 10. So we can do normal CDF. Okay? Now, in order to see this, and let's graph this, but to graph it, we're going to have to convert it to z-scores. So our picture would look like this. There's a z-score of 0, 1 to the right and 1 to the left. Dead center would be 11%. We need to find the magnitude of the step. And we're going to see what's the likelihood that we're out here at 15% or more. Okay? So on the calculator, to find the magnitude of the step, we take the square root of the sample size times probability of success times probability of failure. And we're going to store that in alpha S. So in our picture, we've got 11 children in the center, and the step is worth 3.128. We want to find what the z-score is for 15. So the z-score would be 15 subtract 11. Divided by S, or second answer, either one. So your z-score is 1.27. So if we have this 1.27, we could draw the picture in the normal distribution. Make sense? So we go here. First, I'm going to go to Zoom, Memory, Recall. And that was the decimal, that was the window we set up to draw the standard normal curve. And that stays in there. You don't need to reset this. Once you put it in there once, in the Zoom memory store, it stays there unless you type over it. So I go second distribution, normal CDF, second distribution, draw, shade the normal curve. So where do I want to start with? I want to start with my answer. Second answer, which was the 1.27, the z-score. Now let's come up just with a high z-score. I don't know, 10. Is that logical what we're doing here? Where the center is 0 and the step is 1, because we've standardized the score. Here comes the picture where it changes for you. This is telling you it's a little over 10%. So we got 13% when we did the problem discretely. When we use the continuous distribution, we got a number a little more than 10%. Which is what we got here on the PDF where I said cumulative, go from the left till you get to 15, 11, where the step is the square root of 100 times 0.11 times 0.89, you got 89%, which is to the left. So one takeaway that. You're getting the same answer if you drew the curve, but the issue is if you draw the curve, you have to standardize. You don't have to standardize the scores, but if you don't, you're going to have to rebuild the window every time. So it's easier to convert to z-scores. Now, what happened here? The binomial distribution is relatively new since last week. Then we're taking the problem and converting it using a normal distribution to approximate it. How good a fit is that? And you saw we barely made the condition. Like 11% of 100 is 11, which is very equal to 10. And then the probability when we did the problem discretely was 13%, and when we did the problem continuously, it was 10%. If you had a larger sample size, those numbers would be closer together. Okay? So